Hi there, welcome to this Alchemist Chemistry video looking at directing groups, which relates to the topic of aromatic chemistry and benzene rings. When a benzene ring undergoes an electrophilic substitution reaction, it will have a new functional group attached directly to the benzene ring itself. Now, that functional group can actually alter the chemistry of the benzene ring. More specifically, it can alter the position at which a new electrophile is going to be able to attack and attach itself to the benzene ring in a further substitution reaction. There are two types of directing groups, known as 2,4 directors or 3,5 directors. If this R group was known as a 2,4 director, that would mean it would be encouraging electrophiles to attack this benzene ring at the 2 and 4 positions in terms of further substitution. In fact, if we could encourage even more substitution to take place, it could direct to 2, 4, and even 6 in a tri-substitution reaction. There is an older parlance for this as well. So 2,4 directors used to be known as Ortho-Para directors, as the 2 and 4 position on the benzene ring were known as ortho and para. The other type of directing group is unsurprisingly known as a 3,5 director. Now, if this R group was a 3,5 director, then it would be preferentially encouraging electrophiles to attack at the 3 and 5 positions only, and not 2, 4, and 6. Again, in the older parlance, that 3 or 5 position was known as the meta position, so these R groups were also known as meta directors. Now, I've been saying the R group is encouraging further substitution at these positions. Now, encouraging is a bit of anthropomorphic personification. There's no actual emotions or encouragement going on here. There is some hard fact and scientific chemistry going on behind the scenes I want to emphasize as to why these R groups are directing further substitution by electrophiles at either the 2, 4, 6 or 3, 5 positions respectively, and that's what we're going to dig into right now. Let's first dig into these 2,4 directors, otherwise known as Ortho-Para directors. And so the R group is usually, in this circumstance, known as an electron donating group. Okay, so the R group will usually be donating electron density into the benzene ring structure itself, and this tends to increase electron density in the ring, making it more reactive and more able to interact effectively with electrophiles or maybe even polarize approaching molecules, so they act as electrophiles more easily and readily. So these R groups tend to increase the reactivity of the benzene ring. But I want to show you also why they help electrophiles to attack at those 2, 4, and maybe even 6 positions preferentially. The example I've chosen here is phenol with the OH group attached to the benzene ring. So what's happening here is there's a resonance effect. There's an overlapping of orbitals and the oxygen is able to donate its 2p electrons towards the benzene ring. And so here I've shown a pair of electrons, of 2p electrons on the oxygen being donated towards the benzene ring, and that is causing a resonance effect. It's shifting electron density around the molecule, and so it's pushing electrons from this region here, where we've got this double bond drawn, onto this carbon here. This is why curly arrows are showing. This is going to create our first new resonance structure in the sequence. So once that's happened, you can see this new resonance structure for the phenol has an increased electron density focused on that carbon at position number 2. Well, that would mean that electrophiles would be more able to interact with this region because it's now a better nucleophile than it was before, explaining why the 2 position is preferentially attacked by electrophiles. But then again, if the resonance continues, we can push electron density from this carbon to form a double bond here, and moving those electrons will cause repulsion here, moving these electrons from the double bond position here onto the carbon here, and that would create the following resonance structure. So this is that next resonance structure. You can see now the focal point for the electrons is on carbon number 4. Again, that's going to be an excellent point for the electrophile attack because this now has a greater amount of electron density focused on this point. And then, of course, electrons will move around again. So if our electrons are moved from this position here, the 2 electrons here move from this carbon to form a double bond here, and the electrons in this double bond are pushed onto this carbon here, we get another resonance structure which would look like this. And here in that final resonance form, we can see the electron density has now built up predictably at that position of carbon 6. So as these resonances happen and these shifting of electron density around the molecule occurs, you can see that electron density tends to build up in very predictable positions at the 2, the 4, and the 6. And that's why these points are excellent points of attack for approaching electrophiles, because these are the points which have greater electron density, which can be donated to those electrophiles as they approach to start the electrophilic substitution mechanism off. So with 2,4 directors, usually activating groups involved here, there is a predictable buildup of electron density at the 2, 4, and 6 position in these resonance structures, which explains why these positions are preferred by the electrophile as they attack. Now we're going to look at why there are 3,5 directors and what's going on in that circumstance. Now let's turn to the 3,5 directors, otherwise known as the meta-directors. So here's my example. The R group, in this case, is actually an electron withdrawing group. That means this group is withdrawing electron density away from the benzene ring. That's going to mean there's reduced electron density within the ring itself. It's going to be less susceptible to electrophilic attack, less able to polarize approaching molecules, and therefore generally the reactivity of the benzene ring is actually decreased in these circumstances, making it harder to undertake further substitution reactions. Usually you need more violent or powerful conditions, if you like, to push these reactions through to completion. It has a knock-on effect as well in terms of where the electrophiles will be able to attack the benzene ring based on where the electron density is predictably building up in the resonance structures for this particular 3,5 directing example. I'll take you through that now. The real example I've gone for this time is nitrobenzene with the nitro group attached to the benzene ring. So the nitro group is an electron withdrawing group. It's going to pull electron density away from the ring. So you can see here the resonance structure starting. We've got electron density being pulled towards this electronegative oxygen here, but simultaneously electron density being pulled from the benzene ring structure towards this positively charged nitrogen atom, forming a double bond here. And that will form the next resonance structure in the sequence now. So here in the next resonance structure, you can see a very different circumstance to the 2,4 directors has happened. Once the electron density from the ring has moved to that position there, between the nitrogen and carbon here, forming a double bond, you can see the carbon in this position at number 2 is now left as a positive charge. That is not going to attract electrophiles. In fact, it's going to repel them, making this a very unstable and a very high energy circumstance that will not encourage electrolytic substitution to take place at this position here. So that's why it won't go to 2. Instead, it will try and go to 3, where there's still some electron density left. But again, let's move around again. So once this positive charge forms, it's going to start pulling electrons towards itself. And so it may pull electrons from this double bond here, this pi bond, towards itself, forming a new resonance structure, which is going to appear here. Here's that next resonance structure. And again, you can see once we've moved the electrons from here to that positive charge to remove it, we have now left this carbon at position 4 with a positive charge. Again, that's the high energy, not particularly stabilizing situation. No electrophile is going to be able to attack position 4 because that positive charge is there. Hence, it's going to go to either 3 or 5 instead. And let's finish off this sequence with what happens next, or what could happen next in terms of resonance. So if this positive charge is here, it's going to pull electrons away from this double bond area here. These electrons are moved towards this positive charge to nullify it, and that will lead to the final resonance structure I'll show you now. Here you can see the final resonance structure for nitrobenzene, and again you can see the positive charge is built up on carbon number 6, meaning again carbon 6 will not be a good point of attack for any approaching electrophiles. Instead, it's going to go for where there is electron density still remaining, which is going to be positions 3 or 5, hence why we call this R group a 3,5 director rather than a 2,4 director. I really hope this video has helped to clarify what can be a really tricky topic with lots of quite granular detail going on. If you'd like to know more about directing groups, or more importantly, activating and deactivating groups, of a list of what sort of functional groups or groups attached to benzene rings are activators and deactivators, then please do check out the card for the video on our channel looking at activating and deactivating groups in more detail. Suffice to say, it's been a pleasure talking to you as always, and I look forward to talking to you in the next Alchemist Chemistry video. As always, take care. Bye now.